Okay, everybody getting ready for the fourth reaction that we were studying in this unit. We've looked at single replacements, we've looked at synthesis, we've looked at decomposition, and now we want to look at the fourth reaction, and we're going to be looking at something called a double replacement. And if you look down at our famous Dancing People page that we've been using, we can see down here that you have a dancing couple looking like they're having a lot of fun here. I can kind of fill in this guy's head. And then another dancing couple. And then what do? They switch partners and they do-si-do and do their little swing dancing here. So again, kind of fun thing to way to look at it. But again, what you want to really notice is that how they get together with the pluses and the minus. So that becomes our fourth reaction called a double replacement. If you can do a single, you can do a double. All right, so in double replacement, and again, just to keep in mind also, this is often done in a water solution or an aqueous solution. Okay, and that's what we're going to be seeing. I will post some videos on this on the module, so take a look at it. And for those of you who are in class, you're going to be doing some of this in the lab as well. All right, so what we're going to do is we'll be taking A, B, and C, D. Note the positives and the negatives. Okay, and then what we're going to do is the A element is going to take the D element, and the C is going to collide with the B. Now, again, this is going to be done in aqueous solution, so all of these ions are going to be together. And that's what you want to really, really think about. And if everything goes as planned and there is some type of new compound formed, then A will be with D to form AD, okay, and C will form with B to form CB. Now, just keep a little bit of note on the BC, CB thing. Remember, on a note to the I, it looks like it's B and C. So that typically you may think it's BC, but remember, positive elements are written first. So the C element, which is positive, is going to have to be written before the B element, which is negative, so you get CB. All right, so for instance, let's just say I had some lead-2 nitrate in an aqueous solution, and I had 2 Ki, or I had some Ki in an aqueous solution. Okay, and I was to draw these. What would I actually see, okay, in these two things? Well, the lead nitrate solution would look like this. Now, again, we know that when we put, lead nitrate, which would normally be a solid state, if we put that into a solution in a beaker of water, the lead would be broken off by itself, and the 2 nitrate ions would also be floating around independently. So this would be AQ. And again, they'd be separated. Okay, and if I took 2 Ki, and I'll put that in water, again, this would be a water solution, you would have 2 Ks broken off and 2 Is broken off. So again, notice that in both containers that these ions are independent of one another in the solution. Okay, and they're allowed to move around. Okay, and now what I want to do is I want to pour them together so I can get some collisions. Right, so I want to collision them together. All right, and I would pour them in one large area here. And I want you to notice that one thing happens that's kind of interesting is that the Ks from the Ki and the NO3s from the NO3, they remain dissolved in the solution. Okay, so again, remember, I'm pouring these all together in like the same beaker. Okay, so that means that the KNO3 itself stays dissolved, and that remains soluble. Okay, so the Ks and the NO3s really don't do anything. Now, they may collide, but they have a property such they don't get together. Okay. However, when the Pb ions, okay, the Pb2 plus ions and the I ions connect with each other, again, the Pi is here and the Pb is here, they get together and they form PbI2. However, because of their bond is a lot stronger, what's going to happen here is they're going to precipitate. And what that simply means is they're going to fall out, or they're going to produce a solid. That's what this S means. That S means solid. Okay. All right. And they're going to form something called a precipitate. Now, a precipitate is a solid that's produced in a reaction like this in solution. Okay. And it's going to be a yellow color. Now, you may look at and it will float to the bottom of this beaker or this flask or whatever. Okay. And would not dissolve. Okay, now it doesn't matter how much you heat this or how much you spin this or stir it or mix it. These crystals will remain on the bottom. All right, so that's something to be really important to know about double replacements, is that you must form some type of new substance like this. If you don't, and everything stays dissolved, then you haven't done a reaction. Okay, so it's really important to know. All right, so basically, how do you prove? You want to be able to prove that a double replacement reaction occurs. Now, similar to a single replacement, you have to prove that a reaction takes place based on the chart or the activity chart in table J for single replacement. For double replacement, you want to make sure that you're creating something new, a new substance. Okay, now you can do a variety of things. So if we take a look up here and we finish this reaction, before we look at that, we look at this reaction up here, we'll see that the PB will take the I and form PbI2. So we have Pb2 plus and I2 minus, we can get there. Okay, and then the K and the NO3, and just be careful. Remember, I'm not going to transfer over this 2. Okay, I'm going to call it just K plus and NO3 minus, which is going to be K and NO3. All right, and then they'll crisscross form K and NO3, and then we'll balance the reactions written. However, we're looking for this, right? We want to make sure that we at least produce a precipitate, okay, as a solid before we can say that this is a yes reaction. Okay, so how do you prove double replacement occurs? Well, one of the following 3 things must happen for you to produce a double replacement. Okay, so one of the following new substances must be formed. Now, for number 1, you want to be able to create an insoluble solid, okay, or a precipitate. Now, you may say, well, how am I going to know this? How did you know that PbI2 was the solid and KNO3 stays dissolved as AQ? How did you know this? Okay, well, what we're going to do is we're going to take a look at table F. That's going to be next. Okay, the formation of a gas. Okay, again, you have to know what your gases are. Okay, and again, that would produce bubbles. Okay, and you're not going to be able to tell by looking at a reaction, but you have to know what a gas is. Okay, and if you form the formation of water, and we're going to see this, okay, in some of our reactions. Okay, and here's a little visual on this. You'll see in this reaction where you have a clear and colorless, again, KNO3 is a clear and colorless solution here, and a clear and colorless solution Ki, which is the water part here. So here's the PbNO3, okay, and here's the Ki here. And here you see these crystals being formed, these yellow crystals, which is the PbI2, and they form at the interface. So as those solutions mix, the ions collide and they form those new compounds. All right, so that's going to happen in this. All right, so the next page, or the next slide, is really looking at how do we know? Okay, so how we actually know is looking at something called table F. Now, table F is it's not hard. It's just a little bit complicated to read, so we'll just look at it really quickly. Okay, now in the first, it's really made of 2 charts. It's a chart to the left here, which form soluble compounds and their exceptions, and then insoluble compounds and their exceptions. So it's a little tricky on how it's set up, so I'll just go through it with you really quickly. All right, ions are from soluble compounds, and again, solubles will dissolve. Okay, these are AQ. Make your notes. Okay. The exceptions, okay, are going to be precipitates. So that's what you're looking for to see if you get one of these. All right, exceptions to solubility is precipitate. Again, something that dissolves, the exception is a precipitate. Here, on this side, this is going to form precipitates, okay, but the exceptions are going to be soluble, AQ. So the ideas switch, they flip-flop from each chart. Okay, so for instance, any group 1 ion, okay, is going to be soluble, any one that's attached to any compound. So that could be also potassium, that can be also rubidium. Unfortunately, they don't write that here, but you got to know that group 1 ions, all group 1 ions. Okay, ammonium, nitrate, acetate, hydrogen carbonate. Notice that none of these has exceptions, so these will always be soluble whenever you have them in a compound. Okay, chlorates too. Okay, as far as halides, though, be careful. The halides will generally be soluble, except when they're with the following, Ag, Pb, or mercury. Sulfates, of course, will be soluble also, except when they'll create precipitates when they're with calcium, strontium, barium, or lead. Notice that lead is in both of these. Okay, so really interesting to know. And again, on this side, all of these will be insoluble or precipitates, except when, of course, group 1. So group 1, notice it's always soluble. These will be always soluble, again, with these. Okay, so just be careful on how you read this, and we'll practice in a minute. All right, so for example, let's just say I had sodium sulfate. Well, sodium sulfate, sodium is an ion that's always soluble, and sulfate is always soluble, but because sodium's in it and there's no exceptions, so soluble, you'll always produce separately dissolved particles. Okay, this will always be soluble. Okay, and what does that really mean? That means if you had a solution of sodium sulfate, let's just say you had a little crystal of sodium sulfate and you place that in a water solution, you would have separated sodium and sulfate ions, and this would stay dissolved. This would say sodium sulfate AQ. Okay, however, if you had lead sulfate, notice that lead is here, sulfate is always soluble, but an exception is when you're with lead. All right, so that would be a solid. Okay, so that when you would try to put lead into a solution, okay, it would not break up and it would remain these solid crystals at the bottom, these yellow solid crystals. Also, just confirm on the other page, on the other slide, that PB, that I, is also soluble except when it's with PB, and that's why PBI was also insoluble. Okay, so you're going to have to check on this chart whether you have a soluble or insoluble compound, and that's going to help you prove whether or not you've got a double replacement or not. All right, some tips just to remember this is that, and again, insoluble means does not dissolve. It stays the solid at the bottom. Okay, and again, so it's just a couple little tips. You do not have to memorize this, but I think if you're making your life a little bit easier, okay, in this way, just to remember, if you can remember this, that nitrate and ammonium and group 1s are always soluble, that's going to kind of save you a lot of problems with doing these and consciously going flip-flopping between charts. Remember, those are especially group 1, very common elements that exist in compounds. Okay? All right, so that's really what we want to look on a double replacement and how to read table F. And what we'll do in the next one is do some practice problems. Okay? So we'll take it from there. Have a great day.